Previously, we looked at the development of velocity profile for a fully developed flow, and we came up with this expression here that is Hagen-Poiseuille equation that relates the flow rate through a pipe with the pressure drop per unit length. Okay, so that was the relationship for a fully developed laminar flow. Now let's look at if we can draw something similar for a turbulent flow. For the case of turbulent flow, we again assume a similar system. We have a channel, a pipe that is with a radius d, and here on this side of the channel we have pressure P, while on the other side we have P minus delta P, and then we have an opposite acting shear stress that is tau W. Okay. And if you remember that for the case of laminar flow, instead of looking at this whole channel, we actually look at the differential element inside, or differential cylindrical element. And we were able to do that because for the case of laminar flow, we had parallel streamlines and the velocity is not changing from one point to another. It means that there is steady state flow. While for the case of turbulent flow, as you remember from previous parts, that there is a lot of intermixing, and as such, sorry, as such, the velocity is changing from point to point. It means that if we assume a certain differential volume here, differential element here, it would be different from this differential element, and so with other elements. Okay, it means that we cannot really actually consider differential element and then perform a force balance on that. But instead, for the turbulent flow, we actually perform a force balance on the overall system. Okay. So again, if we try to do the force balance on this overall system, so on this side we have the pressure times the cross-sectional area, that is the force on this end, and then this force should be equal to the opposite forces. So that is the force that is acting on this end, that is P minus delta P times the cross-sectional area plus this opposite shear stress. Okay, so that is tau times the surface area pi d L, that is the length of this channel. And we came up this equation here, that is tau W is equal to delta PD over 4L. And as I said here at the bottom, that for the case of turbulent flow, actually we cannot solve these equations analytically, and I will show you in the next slides why. It means that we have to look at experimental observations and develop some empirical relations. And by doing some experiments, scientists came up with this relation here, that for the case of turbulent flow, the average velocity is actually 0.2 times of maximum velocity, or actually the maximum velocity is 1.2 times of the average velocity. Okay, so this is completely experimental. It is not after an analytical solution. And why we cannot get an analytical solution? So let's look into that. For the case of laminar flow, we replace this value of tau here by using this constitutive equation of Newton's law of viscosity. Okay, and it was possible because we know that the velocity profile is linear, and as such, we can actually, or we know that it was we can because of the layers, we could develop a velocity profile or the velocity gradient. Okay. But for the case of turbulent flow, there are no layers and it's completely random. Okay, it's all disorder. There is no flow pattern. Okay, so as such, we cannot develop this kind of relation that relates tau with the velocity profile. And because of that, we have to again look into some experimental observations and some empirical relations. So one empirical relation that we can use to relate tau with this velocity or maximum velocity is what we call fanning friction factor. And you will look at this fanning friction factor in much more detail in lecture 7, for example, okay, where you will discuss pipe losses and friction losses. So what this fanning friction factor does, it actually relates flow with the maximum velocity, okay. And if you replace the value of this tau now from by using this fanning friction factor and do, for example, compare this equation here, so we can see that we can get a relation between the pressure drop, that is delta P, and velocity, that is actually what we call velocity profile, okay. And this is the velocity profile that we can get for the turbulent flow. But we know that we can also write this delta P in the form of head, that is, for example, delta P is equal to rho G delta H, okay. So that is the head instead of the pressure, okay. So if you divide by rho G, you get the head loss, and head loss is a form of a pressure drop. And again, as I said, you will see this in much more detail in lecture 7. So I'm just kind of introducing this concept here. So this is the formulation where you calculate the pressure drop or the head loss in terms of the friction factor, okay. So by using this equation, you can actually now use the equation of, for example, Hagen-Poiseuille equation, and you just have to put the value of this delta H in that equation, and you can calculate the flow rate of the system, okay. So all the equations that we developed for laminar flow are applicable on turbulent flow. The only problem for turbulent flow is that actually we don't know the relationship between, for example, delta P and the velocity profile, okay. And to get this relation, we have to use empirical relations, and one of the empirical relation is by using this fanning friction factor, and that is the equation here. And how we can get this fanning friction factor, so we have to use again very complicated charts here. For example, this one is called Moody's chart, and again, as I said, you will use this chart and you will discuss much more detail of these friction factors in lecture 7. But just to introduce to this chart to you, so on the y-axis we have the fanning friction factor, at the x-axis we have Reynolds number, and on the secondary y-axis we have the pipe roughness, okay. So pipe roughness is a measure of how much viscosity effect you are going to have, because the more rougher the pipe, the more effect you will have, for example, on the velocity profile from the wall, okay. So these three things relate through this chart. So for a certain, for example, flow rate of the system, you can get um, the Reynolds number, and from Reynolds number you can relate it with the roughness of the pipe, and by relating these two, you can calculate the value of CF. So once you know the value of CF, you can put it in this equation and you can get the value of delta P. And once you know the value of delta P, you can use Hagen-Poiseuille equation and relate delta P with Q, okay. So that is how you can calculate the flow rate of, for example, a fluid if you are in turbulent conditions, okay. So again, as I said, you can use all the equations that you developed for laminar flow. The only problem is that we don't know the value of delta P, and to calculate the value of delta P, you have to use this friction factor. And then once you know this friction factor, you can calculate delta P, and then you can calculate Q by using Hagen-Poiseuille equation. So that is all for this part. So the next lecture will be by Dr. Tom Rogers, and where you will look at conservation equations. And I will see you again in week commencing 7th of November. Okay, where we will look at different applications of Bernoulli principle or conservation of energy equation. Thank you so much for your time.